Hi everyone, welcome back to another episode of the Space Roundup on Space Door Live. Thank you so much for joining us. Thanks for taking time out of your Tuesday evenings. We're back again tonight with another episode with space experts and astronomers Nick Howes and Terry Moseley. Hey Nick, hey Terry, how are you doing?
Hi everybody.
Pretty good, pretty good.
Great.
At least we lunch when we say we're going to.
We do indeed. There is a slightly changed schedule of the Space Roundup over the run-up to Christmas, so check out our social media for the dates in the coming weeks. If you haven't already, please do subscribe to the channel to support our growing community of space fans. And if you haven't also, close enough to Oxford, go check out our new and latest space store in the Covered Market in Oxford. It's right inside the Covered Market, so you won't miss it. I think it's open 10 a.m. to 4 p.m. every single day. So if you're in and around Oxford or a short drive away, please do go check it out. We've got an awesome virtual reality moon experience there, exclusively developed by and for Spaceall. So go check that out if you want to go to the moon, I should say. And yeah, I'll hand over to our experts for the rest of the show tonight.
It really is, yeah, nice one. It really is superb as well. I mean, having been to the Didcot store, I'm going to go up to the Oxford one in a few weeks myself. Oxford itself is an absolutely beautiful city. If you've never been to Oxford anyway, it's absolutely stunning. So, and the Covered Market's right in the heart of the city. So dead easy to get to. As Latch said, we launch on time. Unlike our first story, we've got a lot that we're going to go through again tonight. Some big news obviously been happening over the summer. The biggest one probably is Artemis, and we were hoping to talk about the fact that it's on its way to the moon, and it's all gone a bit Capricorn 1. If you've not seen that film, mid 1970s, it's where most of the conspiracy theories come from. But yeah, so let's crack on. Our first port of call is Artemis SLS. The Space Launch System, which is NASA's new mega rocket. And I say mega rocket, it's actually smaller than the Saturn V, which they launched now, going on for 55 years ago for the first time on a lunar trajectory, as it were. So we had Apollo 4 uncrewed, which is very similar to what this is going to be, 5 and 6. 6 almost shook itself to pieces before getting into orbit, and then Apollo 7, which wasn't a Saturn V, it was Saturn 1B, went into low Earth orbit, and then NASA took what was probably the riskiest step in their entire history in launching Apollo 8 to the moon with a crew on it. So a completely untested in terms of lunar trajectory rocket, in terms of having a crew on it, rocket for the first time being launched all the way to the moon. Roll forward to the early 1980s, and we were talking about this just before we came on air. STS-1, the first space shuttle, that was launched with not only a national hero in John Young from Apollo 16 and Apollo 10, and he'd flown Gemini, and the astronaut as John Young is known. So they put him and Bob Crippen on the first space shuttle. Again, a completely untested vehicle in terms of launch, and launched it. And yes, the first, if you know the story of the space shuttle, probably most of the first 10 of them had some serious problems that could have caused major catastrophes. Obviously, we had the appalling tragedy with Challenger in Columbia later on, but so NASA became very risk averse, and this is what's kind of played into what's happening now with Artemis and SLS. So the Artemis program, SLS program, was kind of a remnant of the cancellation of previous kind of planned mission like Constellation, etc. And it was brought in as an act of Congress in 2010. So we're already 12 years into this program. Now, the current launch was scheduled for just a few days ago, depending on when you're watching the show, and was the second time it had been scrubbed in just a matter of weeks. The first time, and anyone who's driven a Ford car will probably appreciate this, due to a faulty sensor. So temperature sensors can go on cars and give you all sorts of incorrect readings. When a temperature sensor goes on your car, you don't have to roll back basically an £8 million in weight rocket back to the largest building ever constructed, single-story building ever constructed at a cost of tens of millions, which is what's happening now with the SLS. So the first one, they literally could have launched potentially. It was a faulty sensor. Left it out on the pad, kind of recalibrated, etc. Got it ready to go again, and just a few hours before launch again, it was determined that there was a fuel leak on one of the hydrogen inlet valves, and basically they had to scrub again. Now, unlike the previous one, they could have potentially looked at and fixed the leak. They'd looked at all sorts of options, maybe letting the temperature warm up around the rocket, maybe the leak kind of fixing itself. But then you've got echoes to Challenger and what happened there with STS-51L, horrible, real tragedy, loss of 7 lives on that one, and that was due to one of the O-ring seals on the solid rocket booster failing due to temperature issues. Now, the thing is with this whole mission, the cost overruns are astonishing anyway. I mean, Boeing are up against the wall, shall we say, in terms of pretty much everything they do at the moment. But right now, between Boeing, Northrop Grumman, etc., there's a whole lot of problems going on with SLS. This thing is already 5 years and 16 slips late as it is. They've had issues with static fire. They've had issues with launch, on 2 occasions now. And don't forget, the cost of this is anywhere, depending on who you believe, between $2 and $4 billion per launch. Now, if it's $4 billion, we're talking about over 4 times the cost of Apollo per launch. Now, given that Apollo, they were writing the book, literally, and it was a completely new concept. It'd never been done before. And they were having to literally invent the wheel, as it were, in terms of both mission control, ground control, the launch vehicle, the launch systems, everything about it. With this, they should have had 55 years of a bit of know-how and experience as to how this can be done. It's a rocket. It's got SRBs. The SRBs successfully used hundreds of times with the space shuttle. So this cost overrun is kind of, given that we're in the middle of the biggest cost of living crisis in living memory all over the world, and especially here in the UK, it's really catastrophic. And we just had a new Prime Minister sworn in today, so hopefully, better news will come from that. But essentially, the cost overruns on this, there's been all sorts of people, like the Planetary Society have called for it to be cancelled many times. The impact on other NASA missions is another thing. And this is, don't forget, an uncrewed test. This is the first attempt that they're going to get, essentially just to orbit the moon. They're going to do what Apollo 8 did back in 1968 in Christmas with a crew of 3 on it. Orbit around the moon. Basically, it's going to go further than any Apollo mission ever did in terms of orbital distance from the moon, in terms of where it's going to be relative to the far side of the moon, as it were. But 3 million liters of liquid oxygen and liquid hydrogen that are going to have to probably detank now and then put it back in, and then the costs are astonishing. They really are astonishing. And it's not fair to just go on about the cost of this. It is the overall risk aversion, I think, is one of the key things here. Now, you can appreciate why NASA want to do this. They've obviously had 2 catastrophic tragedies throughout the history with Columbia and Challenger, as I said before. They don't want another one. If this were to go bang on the launch pad, you'd kiss Pad 39B goodbye. It would be gone. There'll be nothing left of 39B. We're talking about an absolutely biblical scale explosion here. But between 2 and 4 billions per launch, Elon Musk, not flavor of the month for most people because of Starlink, but he's estimated that he can put Starship into orbit for anywhere between 200 and 300 million per launch. Now, still not an insignificant amount of money, but you're looking at anywhere between about 1/10 to a 1/6 of the cost of SLS. So there's all sorts of rumblings as to whether or not, like certain other large infrastructure projects in this country, HS2, for example, as to whether or not we should actually be, or humanity should actually be, or NASA should actually be still doing this. Is it just a prestige thing? Is it just a national pride thing now? I mean, there's nothing wrong with Orion. The capsule on top, it's superb. It's flight tested and proven already. The ATV conversion that they've used for the service module, again, it's proven technology, so looks really good. The cryo booster, not a lot can really go wrong with that, you would hope. It just seems to be the main launch elements, and again, these aren't reusable, unlike SpaceX's missions. So we've got essentially antiquated technology, and there was all sorts of talk about Boeing kind of refusing to look at refuelability and reusability in orbit back in the day, because they didn't want to. They just wanted to rack up the cash, as it were, in terms of getting the launch vehicle up there. I don't know what you think, Terry, but that to me is and I've talked to friends at the European Space Agency as well, kind of off the record about this, and they have the same opinion. They just see it as, it's kind of like they've got to do it because they have to now, but why? Why is it? It's so over, so expensive, and potentially, they were saying they wanted to get boots on the moon. First female astronaut, first astronaut of color. Putting men back on the moon, as it were, 50 years on from Apollo 17. It's looking like this is going to be 2026 realistically before we're going to see anything like that. I don't know what you think, Terry.
Yeah, absolutely. I've seen a figure that they're estimating it'll be 93 billion total by the end of the program in 2025. And if you divide that by the number of launches, then that'll be 4.1 billion per launch.
Per launch, yeah.
So that is well above, orders of magnitude above what Elon Musk would be able to do it for. But as you say, they've come so far, they can't really pull out now unless, as you say, it goes bang on the launch pad, or, during the mission, hopefully not. But they've gone so far, it's a case of you have to throw good money after bad, if otherwise you've wasted everything you've spent so far. A lot of people are wondering, though, why, since this mission isn't actually going to land on the moon, you don't need to worry about the phase of the moon or anything. And the moon is always there. It's always orbiting the Earth. Why can't you just fix the leak and then send it out the next day, or as soon as you get it back out onto the pad?
It's the batch. There's
a whole lot of other issues.
Batteries,
some of them other people don't even think about. Obviously, there are other launches that they're in the queue. And once Artemis is off the launch pad, they'll be able to launch. They need to get them out of the way. But there are other things like, for example, being able to launch through a relatively low risk area in space in terms of space debris. You can't just say, right, we're ready to go, like the blue touch paper, if there's a whole host of debris up there that you're going to be flying through. So there's those factors and others. We haven't time to go into them all. So it's not just a matter of saying, as soon as we fix the leak, we go. Apparently, the launch, they are reckoning that the next launch window in terms of other factors is the beginning of October. So in theory, they could launch any time after that. But because they need to get these other launches out of the way first, it's more likely to be the middle of October.
Yeah, so you're looking at a 6-week hold, and you were saying about the debris issue. The other one is the batteries. So the termination batteries, the abort batteries. Basically, if they are more than, I think it's a week on the pad, they have to be recalled anyway. They have to be recertified, because obviously, if something were to go wrong and they'd have to terminate the mission, at some point over the Atlantic, essentially blow it up before it caused any catastrophic damage further downrange. Essentially, those batteries have to be recertified. And then we were talking again off air. There's an awful lot of ancillary missions which are attached to this. So you were saying before, Terry, about some of the CubeSats, and I've had a bit of personal experience on this from work that we were doing on Snoopy and the hopeful kind of identification of the Apollo 10 Snoopy module that we believe is still floating out in their orbit, and we believe we kind of knew where it was. And one of the ideas was to send a kind of lowish delta V, lowish kind of velocity CubeSat mission from the Artemis, from Artemis 1 or Artemis 2, on its way to the moon to do an intercept. But the problem is with the CubeSats, they have very limited power capability. They're only like 10, if you don't know what a CubeSat is, it's 10 centimeter kind of by 10 by 10 small satellite. And that's going to be used, we'll be talking about one of the other missions where that's going to be used pretty soon. But these things are absolutely remarkable in terms of what they can do, but they have limited power compared to obviously things that are powered on hydrogen fuel cells or nuclear RTGs, etc., some larger spacecraft. And there's a lot of those that are sitting on this mission that now have got to basically wait for another 4 weeks, because they're not going to let Mr. and Mrs. CubeSat from whatever university in the Okie from Muskogee go along and say, oh, we need to reconfigure our CubeSat. They're just not going to let them have access to them. So they're stuck losing power literally on a minute by minute basis. I don't know. Any other thoughts, Terry, on this?
Yeah, they're ancillary, as you say. They'll let them fail if necessary. The main thing is to get that off to the moon, round the moon, and back again. And if your CubeSat hasn't enough battery power, we're sorry, but you can't have everything.
Yeah, we're sorry, our bad. It's like that scene in The Martian. Like, we're sorry, our bad. We left an astronaut on the surface of Mars. But there you go. Watched it again the other night. What a great film. That and Capricorn one. Brilliant film.
Yeah.
So we'll keep an eye on this one. Hopefully by the time we're next on air, it will have launched. It will be hopefully in lunar orbit. We don't know. It could still be. We might even have a launch party. It might be going up the day that we're on air.
I don't think so, Nick. I mean, it's 6 weeks probably. We'll be back in 4.
Yeah, possibly. Yeah.
Well, at least we'll have some more update on the news and probably a definite date for launch by then.
Yeah, you would hope. Yeah. You would hope. We do want to see it go, but it's ironic that they've got that "we are going" and people have been putting memes like, "Well, back to the pad, back to the VAB." Anyway, moving on to a vastly more positive story. This one's a good one from you, Terry.
Yeah, indeed. Our good friend Mars. 2 aspects, 2 good stories. Perseverance, I think most people are aware, it has been busy on Mars. The helicopter has been busy. The latest interesting finding among a whole lot of interesting findings is that it has found volcanic rocks in Jezero crater, which is where it's exploring. It's a 28-mile diameter crater. They were almost certain it was once filled by a lake. There's a river delta flowing into it, and Perseverance is exploring around the area where the river delta flowed into the crater, thinking that where there was flowing water, sediments and so on, a very good place to look for traces of life. Of course, the water's all gone now, but you would expect in the bed of a dried up lake to find sedimentary rock, and of course that's what they found mainly, but they've now found 2 significant amounts of volcanic rock, basically basalt igneous rocks, which indicates that they've come from a molten interior. They're not metamorphic rocks, they are what we would call volcanic. They have come from a very hot source somewhere within Mars. At least we can't think of anywhere else that they could have come from. So the sedimentary rocks, they think, were about 3.7 billion years old. At some stage, volcanic rock appeared in this crater. It was then overlain by the layers of sediment, and that once that sedimentary rock dried out, basically it becomes dusty, and the winds on Mars blow the dust around, and dust can be a very wind-blown dust can be a very efficient erosive material, and basically it has scarred away a lot of the surface sedimentary stuff on that crater and has exposed these two particular areas of volcanic rock. They think they've named them, forget the origins of the names, but basically one called SETI, C-E-I-T-A-H, which is rich in olivine. That's a magnesium iron silicate. And another one, M-A-A-Z, which I think is pronounced Maz simply, is lava, and that has flowed over the top of the SETI rock. So what we've got there is, in the midst of a sedimentary filled crater, two pieces of volcanic rock, and they think they are actually exposures of a 1 kilometer long ridge of volcanic rock, which has been uplifted at an angle of about 10 degrees. So what? We get lots of volcanic rock here on Earth. Well, the difference is that Earth has an awful lot of volcanism. It has tectonic movements, a much hotter, more active core. And the tectonic movements on Earth can certainly cause lots of uplift. That's what gives it our mountains and so on. But as far as we know, there's no tectonic activity on Mars, or at least there hasn't been for a very, very long time. We can't rule it out simply because there was nobody around at the time. But the theory says there shouldn't have been any significant tectonic activity on Mars. So how did these ridges of volcanic rock appear in the middle of the crater? And the whole point about science is, when you find something interesting, it's not confirming, oh yes, we knew that. It's providing you with something new to think about, and you have to get your thinking cap on and start doing experiments. They will eventually, of course, bring back samples of these, and that's something we'll talk about on another day with the Mars Sample Return Mission, and they'll be able to examine them in lab and get a lot more history. But it's a fascinating discovery at the moment to find these volcanic rocks in the middle of the crater. So that's that. The other interesting thing is that it's simply a year's completion of a very important experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. Now, I don't know why they came up with MOXIE. If you take all those initial letters, you actually get Moisrue, M-O-I-S-R-U-E, but maybe that's too much of a mouthful. So MOXIE it is, the Mars Oxygen In Situ Resource Utilization Experiment. And as it says on the tin, it's to try and produce Mars oxygen on Mars by using the available materials. It's basically powered by a 300-watt heater. What it does, brought by to Mars, obviously, on the Perseverance lander in 2020, and it has been producing oxygen ever since then under various conditions by extracting it from the carbon dioxide in the Martian atmosphere. So what it does is draws in the air with the CO2 in it. It filters out any contaminants such as dust. It then compresses and heats it using a solid oxide electrolyzer. And that splits the carbon dioxide into carbon monoxide and oxygen ions. And those ions are then isolated, and the oxygen ones are recombined to form molecular oxygen, or O2. And that, of course, is essential for any long-term activities on Mars. There's a limit to the amount of oxygen you can bring with you from Earth. So if you're going to have a permanent base on Mars, you need a whole lot of things from the local materials, but one of the most important, obviously, is oxygen. So this has been running away, not continuously. They have been testing it for periods of about an hour or so at a time, at different times, using different techniques and so on. And all of them have worked, and altogether it has produced enough oxygen for a single astronaut to breathe on a daily basis. They say roughly equivalent to the oxygen produced on Earth by a small tree. So they haven't been running it, as I say, 24 hours a day ever since. They wanted to test it under a variety of different conditions. It has been running day and night, and it's been working all the time. It doesn't need solar panels to work because Perseverance is powered by an RTG. And as I say, this draws 300 watts. You need quite a bit of heat actually to split the carbon dioxide. So it's doing that. And what they're going to be doing now is testing it in another set of conditions. They're expecting a very high pressure to be building up in Mars due to the Mars seasonal variations. They also want to be able to test it during rapidly changing temperatures, such as you get at dusk and dawn and so on. But so far, basically, MOXIE has worked exceptionally well. It's been going for a year and has done everything that has been expected of it. And as I say, there are more tests to come, but it looks very promising. So if you had quite a few of those on Mars, you would be able to produce enough oxygen for a crew on at least a sort of a medium-term basis. So Nick, I'm sure you have lots of views on what's happening in terms of sending people to Mars.
Yeah, it's amazing. As you said, you scale this up and you go back to, we were talking about the Martian before. The technology, some of the technologies that Andy Weir proposed in the Martian were vetted and checked by people at JPL, etc. He got a lot of it right. And one of the key things is obviously production of water, production of oxygen on the surface of Mars, which, as you said, is going to be critical. And knowing that there are substantial bodies of ice, slush, water, whatever you want to call it, be either subsurface on Mars or at the poles, again gives you that almost little bit of security that there's going to be a way to generate enough to put a crew on the surface of Mars for what is potentially going to be a year-plus long mission, depending on orbital trajectories and how advanced we are by the time we do a Mars mission with orbital transfers between the Earth and the Mars system. Going back to the volcanic one, though, what I find most fascinating about that is that you've obviously got three of the largest volcanoes, well, the largest volcano in the solar system on the surface of Mars anyway, in Olympus Mons. But as you said, there's been no tectonic activity detected, obviously, since humans have been landing on Mars and putting very delicate seismometers, etc. It's very minimal seismic activity, which goes into the whole methane release story and whether or not the methane is abiotic or biotic, etc., and what's causing the methane releases that we're seeing on Mars. But obviously, if you've got very detailed spectroscopic analysis from things like HiRISE and the other orbiters that are going around Mars now, and obviously you've got the trace grass orbiter, you've got all sorts, but some of the detailed surface-based spectroscopic analysis, and if you could land something into Olympus Mons and start drilling into that and doing things like comparators against these volcanic rocks that have been found. Don't forget, we have no idea what was happening on Mars several billion years ago in terms of volcanism. We know that there's 3 giant volcanoes in the fastest bulge region, but what else was happening? We just don't know. It is really, really interesting. And one, I think that, again, it goes back to, we've got to put boots on the ground. You can send as many rovers as you want, but the reality is that human beings, human geologists are going to be able to do so much quicker. So much there, so much faster. I don't know if I know you agree with that, Terry, but I know there are very, very high profile figures, notably Professor Sir Martin Rees, who are vehemently opposed to the prospect of sending astronauts anywhere ever again. And it should all be virtual reality and robots, etc. It leaves me cold, just the thought of that. But I don't know what you think.
Yeah, it's in our genes, I think, quite apart from the benefits of the science. I mean, we would have never discovered the other continents on Earth if people hadn't had. When you think of it, setting off as, Columbus probably wasn't the first, but is the best known, to sail for thousands of miles across a huge ocean, not knowing what was on the other side. It takes a huge amount of guts to actually do that.
There's a few Vikings who probably object to that.
I know. Well, they took the northern route, which is a bit shorter, but they were sailing out of sight of land. They didn't know what was on the other side. They didn't know that Greenland was there. When they left Greenland, they couldn't see Canada. So you are taking a huge leap. At least we know what's out there when we head for Mars. But yeah, I agree with you. The first missions to Mars will be relatively simple in terms of the scientific experiments to do, but eventually there'll be proper full-size scientific laboratories on Mars, and that's when we really start to get answers about what happened there, how, if any life ever was there, how it developed. Did it originate on Mars? Did it come from space? The way life on Earth may have come from space. So, as you say, you need the boots on the ground there.
Absolutely. But that's a good one. Moving on to our next story, and this is a bit of a Jim Bowen for anyone who remembers Jim Bowen and Bullseye. DART. Sorry about the pun. So this is NASA's kind of DART mission, which is the, let me get this right, the double asteroid redirection test. So if you've seen that, it split people down the middle of this film, but Netflix last Christmas put out a movie called Don't Look Up. I absolutely loved it. I thought it was brilliant. The irony of what they were talking about against the reality of what's happening and the reality of the political will to do anything about it it doesn't escape anyone. But essentially, they were looking at what to do when a large comet was heading our way. And we've had movies like Armageddon with Bruce Willis, and the hokum that was, and the sheer number of mistakes in that film, which NASA uses as a training video to see how many mistakes you can actually make in a piece of film. And Deep Impact, which is a far better film, scientifically a lot better. So the DART mission is NASA's first attempt to actually try and do something about the potential threat of near-Earth asteroids and asteroids that are going to potentially wipe us out. You only have to go back a few years to Chelyabinsk in Russia. Valentine's Day a few years ago, where basically everyone was looking at one asteroid going that way, which is about the size of a battleship, and then a 20-meter wide one hit the upper atmosphere. Luckily, it didn't hit a little bit further north because it would have done even more damage, but 20 meters wide, you're looking at about just under half the size of the one that created the Barringer crater in Arizona, which is a mile wide, 400-foot deep crater that would have killed everything within about 600 miles. That injured 1,500 people, and it kind of really spurred on, I think, the desire to look at how we can do something about this. So this $330 million spacecraft is going to slam itself directly into Didymos, which is Dimorphos, which is a small asteroid orbiting a larger one called Didymos. Now, Dimorphos is about 160, 170 meters wide. Didymos itself, 780 meters wide. So we're not talking about huge potential planet killers here. We're talking about something that realistically they call like a city killer, or something 160 meters wide if it was solid iron hitting the Earth at potentially 27,000 miles an hour, whatever, could do an awful lot of damage. That's there's all sorts of wonderful online tools. There's the crater impact analysis tool, which you can go on the internet and find, and you can basically pretend that you're going to slam an asteroid into the surface of the Earth, and you can hit igneous rock, you can hit water, and you can see the size of the crater. So something 163 meters wide, if it were to land in central London, 8 million people would die immediately. Most of central London would just be a gigantic crater, and you'd be coming out all the way to basically most of the West Country in terms of debris and fallout, etc. It would be catastrophic. So later this month, around about the 27th of this month, early hours of the morning BST, this thing is going to slam into this small asteroid, and they're going to see what happens, because they've got very detailed information now on how it orbits, the orbital time trajectories, etc. And they're going to be looking not only with ground-based instruments, but remarkably, a small CubeSat as well. So the Lycia CubeSat, and you think CubeSats, these are these, as I said, small 10 by 10 by 10 kind of mini spacecraft, but this is going out into deep space yet again, very similar to the ones with the recent Mars mission, which basically imaged as they were flying by Mars some of the aspects of the lander mission. You've got something here which is going to be taking hopefully very high resolution detailed images of the spacecraft crashing into this small asteroid, and it's going to be monitored from the ground. And I know there's a lot of Irish interest in this, although Alan Fitzsimmons is an Irish Terry. I'll talk about a bit more about this in a minute, but there's a lot of kind of British interest in this mission in terms of how we can best warn the world, as it were, and analyze what's going to happen. Now, if you've got something much bigger, if you've got something the size of the primary asteroid here, you're not going to be deflecting it. The reality is we don't have the technology right now to deflect something of that kind of scale and size. Nukes, people talk about nuking them. There's all sorts of talk in various movies about sending nukes at Deep Impact being one, Armageddon being another. You can't really do that. Landing on an asteroid is hard enough. European Space Agency proved that with like trying to land the Philae lander on a comet on the Rosetta mission on 67P. It's incredibly complex going into orbit, analyzing and getting a landing site. Hitting them with nukes, Minutemans, and the various other nuclear missiles that we've got potentially they don't have the range, so you could fragment something maybe at half Earth moon distance, but then you're just going to pepper the Earth with thousands and thousands of smaller, potentially asteroids. Anyway, I've always been of the opinion that, yeah, this is great, this is a good first step, but it needs more effort, it needs more kind of emphasis being put on it by governments, United Nations, etc. Because whilst the asteroids we have mapped, I say we, astronomers have mapped around about 95% of the potentially hazardous asteroids out there, the over 1 kilometer scale asteroids that are potentially, they could do an awful lot of damage. Anything over about 5 to 10 kilometers, you're looking at a global killer, as it were. You're looking at something around about the size of what hit the Yucatan Peninsula 66 million years ago and wiped out 75% of all life on Earth. In the 1 kilometer kind of range, you know, something that size hitting North America or even hitting the oceans. And don't forget, 75% of our planet's covered in seawater, but you only have to watch Deep Impact to know exactly what happens when a large object hits a large body of water. You're creating gigantic tsunamis going in all directions. We don't want that, because you only have to go back to Boxing Day a few years ago, and 250,000 people died from a tsunami that was only 30 feet high, not 1,000 feet high, traveling at 1,000 miles an hour. I think comets are still the bigger threat, and that was very definitely highlighted in that film with Leonardo DiCaprio over Christmas. We need more effort. I don't know what you think, Terry. It's a great first step, and hopefully we'll get some fantastic science from it, but are we doing enough?
Yeah, I agree. The problem with the comets is that you get much less notice of one that's going to hit, because they're coming in from the outer solar system, and you'll be very lucky to detect them with more than about 3 or 4 years warning. Whereas with an asteroid, just to go back to what you're saying, you certainly can deflect this one. They're hoping to change the orbital period of it around its parent body by 10 minutes. The orbital period is 11 hours, 55 minutes going around Didymos. So they think that the impact will change that orbital period by speed it up by about 10 minutes. That's easily measurable. And certainly, assuming that works and you get enough time, you can certainly deflect an asteroid the size of Dimorphos. And of course, the size and frequency ratio is a bit like finding stones on a beach. Lots of small ones, not quite so many medium-sized ones, and fewer big ones. And that's more or less the way it is out in the asteroid belt. The small ones can do a bit of damage. It's the big ones that do a lot of damage. The thing about the big ones is that we're fairly sure that we have found most of the big ones. The larger size of the medium ones are sort of probably the danger ones, between 0.5 kilometer and 1 kilometer diameter. The thing about them is, because they're relatively big and relatively bright, we will probably be able to detect one maybe, with at least 30 years, maybe 40 years notice before an impact might occur. And I would reckon that if you had that amount of time, you could deflect something, even the side of Didymos, if you have that amount of time. But yeah, the thing about comets, as you say, these none of the existing comets that we know of are going to hit Earth anytime in a calculatable future.
It's 8 trillion of them in York.
Yeah, the big ones that come in, like Hale-Bopp, for example. If it had hit Earth, we wouldn't be here talking about it. And we only got, 3 or 4 years notice of that?
No, less than that.
So those are the dangerous ones. But the point is that since you can't detect them until they're about 3 or 4 years from impact, there's not very much you can do about it, except, as they say, put your head between
your legs and kiss.
Kiss, you know what, goodbye.
Goodbye, yeah.
But yeah, the asteroids are definitely a threat. They are detectable, and they are deflectable within certain size range. So this is a very important mission. And it's basically a test, as it says, to see what happens. We don't even know what Dimorphos is made of. Is it a rubble pile? Is it solid? The name Dimorphos seems to indicate that it's made of two separate chunks, 2 different types of material. We don't know that for certain. Will the impact create a crater in it? Will it sort of disappear inside it as if it was sort of very, very loose, rubbly type material? Will it cause a big fracture? We don't know. Hopefully the CubeSat pictures will tell us that. But what happens to Didymos, not just in terms of how much it's deflected, but the effect that an impact has on the surface will give us a lot of information about what we might do in future if we ever had to deflect one for real.
Yeah, and the European Space Agency is sending a mission in 2024 called HERA, which will then fly out to the Didymos Dimorphos system to look at this crater impact in more detail and see potentially what size. I mean, this is the other thing. It's an incredibly complex mission anyway, because you're throwing essentially a half a ton satellite traveling at 4 miles a second into something that's only 163 meters wide and trying to make sure that you hit it at just the right point on its surface, that you cause the maximum amount of, or the right amount of deflection that can give you half decent scientific data. I mean, if you were to kind of just miss or kind of give it a glancing blow, as it were, it's going to completely change all of the orbital parameters and characteristics anyway. And you only have to go back to 103P Hartley 2, the comet mission, and what the kind of precursor to that, when again NASA flung a coffee-sized table object into a comet to kind of get more detailed spectroscopy from it. Again, with this, once they've crashed into it, they're going to be able to, as you said, analyze more of what's in the interior, because there's a stack of meteorites behind me in the cabinets there. You don't know what's inside them. Essentially, you know that they could be predominantly iron, predominantly nickel iron, predominantly rocky. Could be a palisite full of gemstones. You just don't know what's realistically inside. You can see the surface, but the surface on these things, 4 billion years of floating around the solar system, they're covered in dust anyway. So, as you said, Terry, you don't know if it's a rubble pile or if it's something a lot more dense or a lot more complex. You can work out from the mass of the object and the orbital period, approximate densities, etc. But there could be any number of hotspot regions which are, just a dense lump of iron on a rubble pile. You don't know. You have no idea what the whole thing's made of. So it will be fascinating to watch. And the scientific data, I think you were saying that Alan Fitzsimmons is going to be in Belfast giving a talk at Queen.
Well, he's based in Belfast. Yeah. He's giving a lecture to the astronomy group that I'm part of on it just after the mission, but he has been deeply involved in it. I don't think he's a principal investigator or anything, but he is a well-known expert on the subject. So we're looking forward to him giving us his views on what has actually happened. The thing about this is, as you say, it's relatively small object. About they call it the size of a fridge. Now that's an American fridge. It's a bit bigger than the average English fridge or British fridge. But as you say, it's about half a ton, 570 kilos is the mass that'll be left when it hits it. So I don't know what the mass of Dimorphos is, but it's a heck of a lot more than half a ton. So it's really. It's not guesswork, but it's inspired guesswork to say how much it's going to change the orbital period. But the whole point is do it and then see what happens. They'll be able to measure the change in the orbital period extremely accurately, and that will give them the results they want then.
Yeah, they've picked the right combination here, definitely. It's not the science from this. I think the science in this is going to be beautiful, and I think it's going to deliver an awful lot in terms of really good data back to the scientific community. It's what next? It's like with the comets. You're saying about 3 to 4 years. Sometimes it's a lot less than that. When the comet crosses the ice line, typically you're looking at 9 to 10 months away. Now, when we've got things like the James Webb obviously in orbit now, and thermal infrared capability, near infrared, mid infrared capability on the James Webb, that could be extended. You could be picking up objects a lot further out, but it's not really a survey telescope. It's a very narrow field telescope. You still need wide field surveys that have got that real deep space capability to say, okay, something's out of the orbit of Pluto. We've got to keep an eye on this. The orbit's looking a bit iffy. If it passes by Jupiter at a certain distance, maybe Jupiter will deflect it, and maybe then it'll light up, and then all bets are off. Obviously, when the comet starts jetting out, you get orbital changes again there. So I think we need almost like a deep space network of telescopes akin to the James Webb, obviously not on that scale, but something maybe at Lagrange points around Jupiter or somewhere stable that you can point them out towards Oort cloud / Kuiper belt areas, maybe dotted around the solar system, so you can say, okay, let's keep an eye, because one of these days something the size of Hale-Bopp is going to come our way. And it's not just that. You talk about all the asteroids in our solar system. What's it, Urimama? I Forgot.
Yeah.
Yeah,
Extra,
that thing that they
extra solar
thought,
system. And,
exactly. They thought that it was an alien spacecraft because it accelerated, which is ridiculous. But that changed, don't forget, its orbital kind of velocity as it was nipping through it was accelerating as it was going through the solar system, and they still couldn't work out why. But again, we're now finding extrasolar asteroids coming in at astonishingly high velocities. So if one of those, something the size of that one were to hit the Earth, there wouldn't be much left of the Earth, let alone life on it. It's just be
fortunately, they are pretty rare. So
fortunately they are, but as I said, there's 8 trillion comets out in the Oort cloud. Good luck on that one. Please, we've seen, thanks so very much seeing people in the chat, Ground-Based Space, Rob Thomas, Rachel, Daydream Astro, brilliant to see you all here. Thank you so much. Please fire in questions. We love answering questions. We love kind of going off on tangents and stuff. I know Ground-Based Space has said, yeah, China will probably get there first. Possibly. I think SpaceX, that's the race.
Yeah.
Going back to the Artemis story, it's SpaceX versus NASA. Maybe China. I don't think for lunar, possibly for a robotic lunar lander yet. I don't think for human landings that they're going to be directly up against NASA in this case. SpaceX, yeah, all bets are off on that one. Anyway, moving on to our last big story, and this is quite a sad one, but it does link on to some fun stuff. The passing of Frank Drake. Over to you, Terry.
Yeah, lots of people who have, in fact, almost anybody that has any interest in this will have heard of the Drake equation drawn up by Frank. Now, it's not, well, it is a sort of an equation. It's just a way of trying to analyze and eventually put figures in all the different factors that go to make up the chances of there being another communicable alien civilization that we can get in touch with. And I'm not going to go through it all. You can Google it. A lot of the things have changed, but basically it's based on the number of stars being formed in the Milky Way, the number of those that have planets, the number of the planets that might be habitable, the chances of life developing on any of those planets that are habitable, the chances of that life becoming intelligent and technological, and then probably the most important factor, because we think there's a reasonably high probability of the ones I've mentioned so far, the expected lifetime of that civilization. How long will a technological communicating civilization last for? Because if there's one that has been and gone and we didn't happen to catch their signals as they went past us, well, that's it, they're away to elsewhere in the universe. So fascinating subject. The interesting thing is that with the development, for example, of the super telescopes that we have here on Earth, like the VLT, the EALT coming along, Hubble out in space, James Webb out in space now, we're being able to get a huge amount of information on the number of other planetary systems out there. And of course, I have to mention the Kepler spacecraft was designed specifically to detect those planets. And we now think that basically most stars in the universe have planets. The star itself may not be suitable for being a host star for life. It may be too violent, too hot, much too small in terms of the lifetime, the amount of energy it produces, too big and too speedy in terms of its nuclear reactions. But there are a large number of stars out there that have planets, and we know already of hundreds that are in the habitable zones of those stars. And that leads on to another well-known quote, if you like, in the whole SETI question. If the universe is full of aliens, where are they? So we haven't detected any, but what Frank Drake did was attempt to put a very strict, rigorous scientific analysis on the question. And as I say, we now can fill in quite a lot of the figures in the first elements in the equation. The last one, the lifetime of a communicating civilization, is the one that we can only guess at. We have only been communicating for roughly the last 100 years or so in terms of radio signals going out into space. Who knows, in, say, even only another 100, 200 years, will we still be using radio at all? Or will everything be done by, for example, fiber optic cables, so that any signals that we send out would be ones that we would send simply deliberately to try and contact anybody else out there? So an absolutely fascinating subject. the time question really is one that an awful lot of people have difficulty getting their heads around. We're here, you know, if they're out there, why can't we hear them or see them or send a signal to them, get a reply back? The universe is about 13.8 billion years old. Now, for a whole lot of reasons that we don't have time to go into, there wasn't going to be any intelligent life developed in probably the first couple of billion years during the lifetime of the universe, because intelligent, advanced technological life like us needs a certain proportion of heavy elements in the planet that it develops on. And they are produced in series by a whole sequence of explosions by supermassive stars, which create those elements, blow them out into space, and they then form planets going around other later generations of stars. And you need multiple generations of that happening before you get enough of the heavy metals, for example, the steel, the iron, the other important elements that we have, even the iron that we have in our blood, never mind the iron that we use in engineering. So it's probably only being conservative in the last 5 billion years or so of the universe's existence that you're likely to have got other advanced technological civilizations developing, because there simply weren't the materials, the raw materials there before that. But 5 billion years is an incredibly long time. It took about roughly 3.5 billion years for intelligent life to develop here on Earth from the very first primitive life forms. But it could have happened on another planet 1 million years earlier. Okay, so say, taking a well-known example, there's a planet going around our nearest other star system, Alpha Centauri and Proxima Centauri, and say, it's very unlikely actually, but just say for the sake of argument, that a civilization developed there 1 million years ago. If it only lived for even 500,000 years, those signals have passed us by. They're gone. We will never, ever know. So not only does there have to be another intelligent, advanced civilization in our vicinity, it needs to be at just the right distance from us for the signals to be reaching us during the period when that civilization is communicating. And that is the important thing. So we're due to discuss this back and forth rather than either one of us sort of pontificating about it. So I'm sure you would have your own thoughts on that aspect of it, Nick.
Yeah, it's wonderful. I mean, it's sad the passing of Frank Drake, but obviously the spin-off work with SETI and people like Jill Tarter and Seth Shostak, etc.
Yeah.
I mean, his pioneering work really did inspire so much in so many people, you know, through to Sagan and Contact and, you know, so many different aspects. The thing with the radio discussion, and this is what I've talked to Jill Tarter about this in the past, it is this kind of very narrow window, as you said. You know, we've had 100 to 150 years, Marconi onwards, you know, since we've been able to, you know, transmit and receive radio signals of any kind of magnitude that could be detected by even local star systems and planetary systems. And that whole kind of shifting window between the different planetary systems. What's interesting, you touched on it before with Kepler, is some of the great telescopes that we now have, and ELT is one, OWL is another, the overwhelmingly large telescope, and some of, you know, obviously the planned future space telescopes, James Webb, hopefully just the first big step into large structures. If we get Starship and SLS being able to, you know, the larger fairings on those, being able to put even larger telescopes into orbit, you know, the James Webb being a phenomenal success in the way that it's deployed and unfolded. This ability to, and we're going to move on to that. We'll actually move on to that now with our next story. And this kind of ability for these large telescopes to detect exoplanets, directly image exoplanets around orbiting star systems, is quite astonishing. And it's been done a few times. You know, James Webb it was almost the kind of like, oh, we can do this. You know, for something like the Hubble, this was incredibly complex. And as you said, we've got several thousand exoplanets have now been detected, but mostly either through Doppler shift or through, you know, orbiting transit, where the light from the parent star dips. Now, if you imagine how complex this is, it's almost akin to, if you've got an average sized star, you think about our Earth can be swallowed by our star 1 million times. So you're looking at a light bulb, basically 1 million times larger than the object you're trying to image, right next to it, at a distance of light years, like hundreds of light years potentially. So this method of being able to occult the star basically block it out. And really clever thing with the instrumentation on both the Hubble and the James Webb is how they do this. But essentially being able to block out the star and just image around it in the orbit, and to detect the exoplanet directly with James Webb, it's almost like, yeah, we've done that. What's next? So hopefully we're going to get hundreds of these direct images from the James Webb. Now, as opposed to radio, if you look at the mess we're creating around our own planet now with debris, that's going to be, for larger telescopes, almost detectable in the not too distant future. It'd be almost like a ring system. If it gets so bad around the Earth, where we've got literally gazillions of pieces of debris orbiting around, you could potentially have, you know, even a transiting exoplanet, an astronomer, say 20 light years away on a nearby planet, looking at, you know, the Earth as it passes in front of the sun and going, hold on, what's going on here? It's got a ring system, but the ring system isn't actually made up of anything, you know, found in nature. There's all sorts of weird metals and materials in this from the spectroscopy. This is based upon looking into the future of where we're heading technologically. If we can image now atmospheres on exoplanets already and be able to detect potentially seasonal variations, maybe indicative of plant life on the surface. If you've got, at this point in the orbit, there's this much oxygen in the atmosphere, but at a different point in the orbit, there's a little bit more, there's a little bit less. There's all sorts of things that we could do, but if you take our technology forward maybe 100, 200 years to where we could be, and the ability with vast telescopes the size of Owl or even bigger in orbit, potentially on the far side of the moon, stuck in a crater, looking out into deep space and saying, okay, we've got a telescope that's essentially 1 kilometer wide, strung inside a crater, being able to do the kind of level of imaging that you'd be able to really almost detect surface features. Now with the Hubble, we can see star spots on, Betelgeuse, etc. But that ability has got to be the way that we do it. The radio idea is just so arcane in this shifting timeline that you've alluded to, Terry. Whereas if you've got an orbital debris mess, or you've got laser transmission, or you've got something pulsing light, or as Kepler detected several years ago, we were thinking about talking about this on the show, but Kepler detected what was called an alien megastructure, because they just don't know what it is, orbiting a nearby star some years ago. That, to me, is the way that it's going to be done. If we're going to communicate with an alien civilization, if we were to detect something at even maybe 20, 30 light years, being able to do pulse beam, if we knew that it was intelligent, and that's the big if. But if we were to detect almost like a primitive Morse code type signal, what we did with Voyager, what humanity did with Voyager, etc., it was really clever in that here's our star, here's where we are, this is the base element, here's the basics of physics and mathematics, which we would hope are universal languages. The basic, structures of atoms, etc., it's across the entire universe. The basics of mathematics, maybe our numbering system's different because we've got 10 fingers, etc., but the basics of mathematics, you would hope, is again a universal language. And this ability for an advanced civilization to send out pulses that are indicative. You look at Jocelyn Bell Burnell and the detection of pulsars, and initially they thought they called it LGM1, Little Green Men, because it was an unusual pulsing star. They couldn't work out what it was. But if you've got something that's sending almost like a Morse code message from a nearby star system in light, or whatever methods they deem the best way to do it, and again, you could just send up a gigantic mirror and just bounce light off the nearby star and say, okay, we're going to angle the mirror almost like you do on the old ship Morse code semaphore systems, where you'd have like a light and you just open and close the shutter. Something akin to that, I think, would be the best way forward in terms of scientific evaluation of the potential for advanced civilizations. Now, the thing is, what we call advanced, we're not even looking on our own planet. 75% of our planet is covered in water. And you look at dolphins, you look at whales. These are intelligent creatures. We can't even communicate with them. We can't even communicate with 99.9% of the other species on our planet. We've only just worked out that dogs cry, in 2022. So to say that, we're ahead of the game in terms of science, we're not. We're not at all. When we can communicate with the other species on our own planet and realize that what we're doing is irreparable harm, maybe we'll get somewhere in terms of alien life. But that, to me, is the way forward. I don't know if you've got any other thoughts, Terry, but I love this. The James Webb images that you're seeing on the screen now, it's just amazing. First hit, like boom.
The advantage of it is that it's imaging in the infrared. Just sort of ballpark figures. In optical light, the average planet orbiting another star is of the order of about 1 million times fainter than the star in visible light. In the near infrared, this particular one, for example, is about 10, the planet is only, in inverted commas, about 10,000 times fainter than the star. And if you go into the mid-infrared, where the MIRI instrument operates, then it's only a few thousand times fainter than its parent star. So if you use a coronagraph, that then gives you, as the photographs show there, actually the opportunity to actually image such stars directly. That, although James Webb is not designed for searching for new examples of this, but one of the advantages that it can do is that it can image a planet like that, which is not transiting its star. That is how most of the exoplanets have been discovered. They're orbiting around their parent star in the plane of the direction to the Earth, so that we see the planet pass in front of the star every so often and the light dips, or associated to that and operating in more or less the same way, even if it's not transiting. If it's a massive enough planet, as it orbits around its star, the two of them are actually orbiting around their barycenter, their common center of gravity, and that makes the star itself appear to wobble as the planet goes around it. But that has to be not exactly, but more or less nearly in the same plane as the direction to Earth for us to get the maximum effect. If a planet is orbiting around another star at right angles to our line of sight, those methods will not detect it. But if there's some other way of detecting that, then James Webb would be capable of doing that sort of imaging with it, which no other telescope can do, because it is so powerful in the infrared. So there are lots of other opportunities there for James Webb. It has shown us what it can do. Absolutely brilliant images, as you were saying. Other telescopes have managed to image exoplanets from telescopes on the ground using special techniques, but they're nowhere near as good as those images. So good old James Webb is certainly living up to its billing.
Well, it's superb because it's follow-on, as you said. We've got data from Kepler, we've got data from Hubble, we've got data from ground-based observations showing us where these exoplanets are. And now, if you just did a survey using the James Webb, even if you don't have direct evidence of an exoplanet, if you picked, say, the 20 nearest stars to the Earth, and just surveyed, use this occultation method, this coronagraph method, where you're just surveying those. Could you imagine what you could find entire planetary systems, at this kind of resolution? And this is the amazing thing. Near infrared, mid infrared, you're looking at vastly longer wavelengths than in the optical and the UV end of the spectrum, which is where Hubble specialized. So the image resolution, the capabilities of the James Webb are just out there. If you then add on top of that things like the square kilometer array and its resolution capabilities, when that's fully operational, which they're saying are 50 times higher than the Hubble in the radio spectrum. And radio, we're talking about not just actual radio waves, we're looking at all sorts of things in terms of planetary atmospheres. It would be incredible. Some of the comments in the chat. Yeah, imagine a day we image a planet is clearly something man-made. Yeah, human-made or alien-made, orbiting around it. Yes, it will change the world. It will absolutely change the world. It will be one of the greatest scientific discoveries in history. But I just think with the early release phase of the James Webb, and I know it's so competitive and it's only got a finite lifespan, but to me, this is one of the big questions. Yes, the universe, the formation of the universe, and all the weird stuff that's coming out in terms of Z numbers and stars forming and entire galaxies forming way faster than was previously estimated. That's definitely part of it. But exoplanets, it's absolutely fascinating. Just get it surveying nearby stars. That's what I'd do. But I'm not in charge of the James Webb, so.
We'd better go on to look up, or we'll be out of time.
Indeed, winter is coming.
the two biggest planets in our solar system are very well placed at the moment. Saturn was at opposition almost a month ago, but is still very well placed. Not all that bright, but you can certainly see it low down in the southern part of the sky when the sky gets dark. If you've never seen it through a telescope, do try and get a look through a telescope at your local astronomy club or wherever to see Saturn and its rings, not on a computer screen, not on a photograph, to see that yourself through the eyepiece against the inky blackness of the sky. Just an exquisitely beautiful object to see. The rings are tilted about 14 degrees towards us at the moment. They're slowly closing. That angle is narrowing. So get a chance to look now while they're still quite good. Jupiter, the king of the planets, reaches opposition later this month. That means it'll be its brightest in the sky. And it's actually, this opposition will be one of the closest and brightest ever. It will reach a magnitude of -2.9, which is the absolute greatest brightness it can ever achieve. And that'll mean that it's second only to Venus in terms of brightness in the sky, the night sky, apart from the moon. Easy to see. It'll be basically blindingly obvious that it's there, relatively high up in the sky, much higher up than Saturn. Beautiful to look at in the telescope. No ring systems that we can see from Earth, but 4 large moons which are visible even in binoculars, and fascinating to watch the way they orbit around. And then later in the night, Mars is coming up, brighter than Saturn actually, brilliant red, nicely placed near to Aldebaran and the Pleiades, and it'll be reaching a very good opposition coming up in December. We'll talk more about that later. But basically 3 of the best planets to view in the sky are around there. Get a chance to look at them. And also we have the start of astronomical autumn coming up with the equinox on the 23rd of September. And from then on, it's good news for astronomers. The nights are longer than the days. Bad news for everybody else. Too much night, not enough sunshine in the day. So you can't please everybody.
Yeah, absolutely. And given our cost of living crisis that's coming,
indeed.
getting outside with a nice warm flask might not be a bad thing anyway. I know there's people in the audience who do a lot of outreach, etc. Obviously, we've got World Space Week coming up and this 100 Hours of Astronomy project coming up as well. Keep an eye out for local events. Definitely, hopefully we're going to be on air before the next one. We'll be able to talk a bit more about that during the next show. But that's something as well. If you're looking at doing outreach events, start your planning now. And start getting the message out via your social media channels, etc. is a really good thing, and it's a great way to get kids into astronomy. Great way to get even the general public into astronomy, especially riding the wave of the interest due to Artemis, the interest due to the James Webb. James Webb obviously also detecting beautifully the ring system around Jupiter. Saying you can't see it from the Earth, you can't see it with the James Webb. It's amazing. That kind of thing really is inspiring. You've got the DART mission. That's probably going to hit all the major news headlines as well towards the end of the month. So all of these hopefully will inspire people to look up at the sky. And the more people we get looking up, the greater chance we've got of stopping an asteroid or a comet from hitting us in the future anyway. We'll be back in about 4 weeks, all being well. And like I said, try and get yourselves up to the Space Store in Oxford. It is really, really fantastic. They do a lot of outreach there. I'm hoping they're going to do something for World Space Week as well. Terry and I mean, Terry's recovering as well from a recent outreach event himself. But he's been an absolute soldier tonight as usual. Brilliant, Terry. We won't go into the details, but yeah, he hurt himself a little bit in an outreach event. So another good thing, be careful when you go out at night. Obviously, there's lots of trip hazards about, etc. Make sure that it's a well-organized event. Get in touch with your local astronomical society. They're always really helpful, friendly, etc. Always love to see new faces, especially young people is always a good one. Thanks to everyone in the chat. Ground-based space, walking. I was out, driving my kids to the airport at ridiculous hour in the morning the other week, and Saturn was just stunning. You could not miss it. And as Terry said, Jupiter, I can't wait to see what the likes of Christopher Coe and Damien Peach and all the great astro images are going to be able to do with such an amazing opposition of Jupiter and so high in the sky. Damien won't even have to go to Barbados and take his shirt off. So it'll be really good. But we are going to end it here, slightly overrun. Massive thank you to the backroom team, new backroom team that we've got, done an absolutely brilliant job as usual. Latch has got another engagement, so it's up to Terry and I to say, and it's good night from him and good night from me, kind of thing. Any final words, Terry?
No, just keep looking up, stay safe, enjoy the sky.
Yeah, absolutely. Take care, everyone. Speak to you in a month.
Bye.
Bye.